Today we're going to be talking about the chain rule, and the chain rule is when we have a composition of functions. So say we're looking to find this, and the only rule that we know now is if we write out the product of the two polynomials, and you write out the product correctly of the two polynomials, and then leaving the first alone, derivative of the second plus derivative of the first, leaving the second alone. So now, look, you have two of the same terms. So I have 2 of 4x squared minus 3x plus 2 times by 8x minus 3. So then we have, so now let's look at this. Where did this 2 come from, I should say? Okay, that 2 comes from there. I bring the 2 down in front. Brought the 2 down in front. Reduce the polynomial by 1 power, and then what is this? Well, that's the derivative of the inside. So let's look at this a slightly different way. So say I wanted to find now this. This is really a composition, f of g of x. So f of x is x to the 100th. G of x is x squared plus 1. We know f of x is 100x to the 99, and g of x is 2x, g prime of x, I should say. So now, if we are looking at this with like a u substitution, we let u equal the inside function. So now we have y equals u to the 100th power. dy du, well, that's that same thing. 100 u to the 99th, du is 2x, so now I have 100 u we said was x squared plus 1 to the 99th times by 2x. How did I get that? I took dy du, and I multiplied by du dx. Okay? And then, I mean, just algebraically, it makes my calculus brain cringe a little bit, but the du's cancel, so we get dy over dx. But just make sure that you're substituting back in your u. And I promise you're going to get really used to these, really comfortable with these. So our chain rule, okay? So when I have a composition of functions, so it's derivative of the outside function evaluated at the inside function times by the derivative of the inside function. So now looking at revisiting this problem, my outside function is something squared. So my outside function is 2 something squared, reduce your power by 1. My something in this case was 4x squared minus 3x plus 2 times by the derivative now of the inside function, which in this case is 4x squared minus 3x plus 2. The derivative, Mrs. Marnell, whew, I'm thinking about the guys that are making a lot of noise outside my window. That's what I'm thinking about. I apologize. So then I take the derivative of the inside function. I promise you guys I know the chain rule. So let's look at some examples. So here we have a product and a chain. So we have a product rule. And then we have a chain rule with the 2x being composed inside the function. So my derivative is equal to, so leaving the first alone. Derivative of the second. Derivative of cosine is the sine of 2x. Now I need to take the derivative of the inside. The derivative of the inside is 2. Plus derivative of the first, which is 6x, leaving the second alone. Now, just simplifying that a little bit, with the chain rule, you don't have to simplify a whole bunch. You just kind of want to, I'll say, clean up the problem. So if I take the 3 and the 2 and I multiply by a 6, you could go ahead and factor out a 6x if you wanted. I would be okay with either answer at this point. Okay, this guy. We have one function on the outside, that's the x squared function, or the square root function, and then we have a function on the inside. So this is not a product rule, this is a straight up chain rule. So my derivative of the outside function is 1/2 the inside function to the negative 1/2 power. My inside function is x cubed plus cosecant x. Then I have to take the derivative of the inside function. Well, the derivative of the inside function is 3x squared. Derivative of cosecant is the negative cosecant x cotangent x. Okay? And I guess you could simplify that by putting this square root on the bottom. In calculus, now we're okay with square roots in the bottom. There's this magical thing that happens once you finish with pre-calculus that we're okay now with radicals in the denominator. I'm okay personally if you leave it like that. I don't really care. Okay? Okay, our next example. We have the sine of some craziness. Then we have the square root of some stuff. And then the innermost function. And for some reason, I always look at these like layers of an onion almost. I have the outside function, the inside function. You keep going through to get to layers of your onion. So taking my derivative of sine is cosine of the square root of 1 plus cosine x. I'm going to clean this up a little bit so I have a little bit more room to work. So I've taken the derivative of the outside. I've dealt with that function. The next function I need to take the derivative of is the square root function. So derivative of a square root function is 1/2 something to the negative 1/2 power. What is that something? That something in this case is 1 plus cosine x. Then I take the derivative of 1 plus cosine x and I get negative sine x. And right now I'm just looking at my answers and I have the same thing that I had when I did these problems a little bit earlier. Okay. Again, I talk about layers of the onion. Remember, tangent to the 5th power really means tangent to the 5th. Then I have the tangent of quantity 6x cubed minus 2x plus 7. So I have 3 colors, so I have 3 layers. So I'm really doing the chain rule 3 times. Derivative. 5 of my craziness to the 4th power. Now what's my craziness? The tangent of 6x cubed minus 2x plus 7. Now I take the derivative of the next layer. The derivative of tangent is the secant squared of 6x cubed minus 2x plus 7. Now, I like this problem because now students want to take the derivative of secant. No, look at the original layers. I've taken the derivative of the outside function, the something to the fifth power. I've taken the derivative of tangent. That's sitting right here. I don't take the derivative of secant squared. I now take the derivative of that inside, that what's in the angle, and get 18x squared minus 2. Okay? So you don't take the derivative of secant. That's often a common question that I get asked. So our next example here, equation of the tangent line. So for the equation of the tangent line, I need the slope, which is a fancy way of saying derivative. I need a point. I know my x-coordinate is pi over 6. Plug in pi over 6. I get the cosine of pi over 3 to the fourth power. Okay, cosine of pi over 3 is 1/2 to the fourth power is 1/16. 16th. There we go. Okay, so now I need to find my derivative. Y prime. 4 cosine of 2x all to the third times by the sine, negative sine, oh, I almost missed my negative, 2x. So I took the derivative of x to the fourth, I took the derivative of cosine. Now you have to take the derivative of the angle, the 2x. Okay, lastly is the derivative of that. One of my favorite questions is to put something with an angle in there because students often forget to do that. So now I need to evaluate my derivative at the x value. So I really have cosine of pi over 3 to the third power times by a negative 2 times by the sine of pi over 3. And that all simplifies, assuming that I did my math correctly, negative root 3 over 2. I'm sure you'll tell me in class if I didn't. Again, remember I like point slope. Y minus y1, which in this case is 1/16, equals slope times x minus x1. Okay, find the derivative of ln of x. And this slide actually, I love this slide for a few reasons. This is my old cat. She passed in November of 2019. So this is my little Bubbles that is sitting in a shoebox. This is one of the ones that I didn't upgrade to. My husband and I, our new cat, I let her still be there so I could see her and she could make me smile. DJ is giving us a hint from across the Rainbow Bridge. She says, write this as an exponential. So e to the y equals x. Now, it's very interesting that our book does this before we talk about a certain type of derivative. So there's a special type of derivative. It's called implicit differentiation we're going to be doing here. So this is a bit of a spoiler alert for our next section. So let's look at this. The derivative of e to the y is e to the y times by dy dx. It's a kind of like a chain rule, really. E to the y, and then I need to take the derivative of y, which is dy dx. So that's what, it's kind of a hint for a spoiler alert, but also now I kind of see why they put it in this chapter. Derivative of a y is dy dx equals 1. Now I need to solve for dy dx. What is y? Y is ln of x. dy dx is equal to 1 over x in this case. Okay, so some of these we have already talked about, okay? Derivatives of natural log functions, derivatives of, we've talked about if they're a different base, okay? And then if the base for a logarithm is not e. So please make sure you have those in your notes. You might need to pause the video. I'm going to keep moving on to some of our examples because I have some good examples happening here. Okay, this first example. Oh, this is my favorite example. One of my favorite examples. I put this on multiple choice one year, and I had half the class coming up to me. You don't have the answer. You don't have the answer. You don't have the answer. And all I did was sit there and smile at them because I'm Mrs. Marnell, and I like to do fun things. Log rules. You can bring down the 2 in front. And then I can take the derivative and get that. Now B, I can't do that. And that's why I want you to also recognize the differences between these two. B is really this. So I can't have 2 equal signs. I guess I could. Bring down the 2, reduce the power by 1, times by the derivative of the inside, which is 1 over x. So some simplifying you can do as you go along, okay? Okay, for this one, this is a product rule. So y prime. Sometimes I do the product rule a little different, meaning sometimes I take the derivative of the first, leave the second alone, plus leaving the first alone, derivative of the second. So sometimes I do that. It doesn't matter which order you do it in. So I like derivative of the first, which is 1, log base 2 of x, plus, leaving the first alone, derivative of the second, 1 over x, ln of 2. Now we can simplify that a little bit. The book is going to do a lot more simplifying, so just as a heads up, that's what I get for that one. For D, okay, this is, we could do this a couple different ways. I'm going to do it the original way that I just saw it and the way that I did it when I made my notes. There's also another way that you could do it using logarithmic differentiation that I'm going to go through on the other slide, on the next slide. So looking at this one, 1 y prime is equal to 1 over my function times by ln of 5 times by derivative of the top. So 1/2 x squared minus 4 to the negative 1/2 times by the derivative of the inside, which is 2x in this case. Now finding the derivative of this, and I kind of talked about this on the last slide, logarithmic differentiation. See how you have an ln and then you have all this craziness? We can use our log rules to break this up. So I can rewrite this function using my log rules. Remember, when we are multiplying, we can simplify under addition, bringing any exponent down in front. When I am dividing, I subtract, bring down my exponent, and we get that. I'm just double checking to make sure I got everything. Yep. Now, it's funny, on one of them, like on the last example, we could have factored that and made it and simplified it even more. So if this factors, then you want to factor it out. It doesn't factor, so we can leave it like that. So now simplifying, I get 1 over x plus a 2 over x squared plus 1. Then I have to take the derivative of the inside, which is 2x, 1/2, 2x cubed minus 1, times by the derivative of the inside, 6x squared. Now we might want to clean that up just a little bit. Minus, that cancels to be 3x squared over 2x cubed minus 1. Okay, next example. Probably one of my favorite examples. We'll do blue for this one. So, finding the derivative with respect to the following combination. Okay, so using a chart of values. This is using a tabular method. So I'm looking at a table of values. Sometimes we might be looking at a graph. Our book has a few of them where we look at a graph. So f prime of g of x, g of, I apologize, 2x, times by g prime of 2x times by derivative of the inside, which is 2. Now I'm evaluating this at 1. So all of this work I want shown. G of, when I plug in 2, I get 2 there. I'm sorry, when I plug in 1, I get 2. So G of 2, G of 2 is here, that's 3. G prime of 2 is 4. I'm going to continue here because I think it would be hard to see if you write on the screen. F prime of 3. F prime of 3 is 5, so I have a 5 times a 4 times a 2. I have in my notes that one of these is negative. F prime of 3. No, I don't know what I did. F prime of 3, yeah, it's 5. I don't know where I got a negative 2 from. Well, I don't know. So I have 5 times 4 times 2, and that ends up equaling 40. Okay, so that is your chain rule and also some derivatives of e to the x functions.